Okay, so now here we are in this chapter 1 on chemistry and measurements, and we've talked a little about chemistry and about how you prepare, and we're finally ready to talk about measurements. So in order to discuss measurements in any meaningful way, we need to have a standard unit of measure for different measurement types. Living in the United States, we're used to very unusual measurements compared with the rest of the world. So units of measure for us are often degrees Fahrenheit rather than Celsius, inches rather than centimeters. The units that we use in science have to be consistent with the units used worldwide, and we use the metric system. And so it's important, at least for this course, that you understand metric measure. And if you're going into the health professions, 37 degrees Celsius is roughly normal body temperature, so quite a bit lower than the 98.6 you might be used to in the Fahrenheit system. So on this slide, we see some measurements that we use in everyday life, only we don't typically use them here in the United States. Walking 2.1 kilometers to campus, that's roughly 1.3 miles to those of us who are used to that system. Carrying a backpack with a mass of 12 kilograms, well, 12 kilograms is about 26 pounds. Kilogram-pound difference is probably the most bizarre to me. I would think that everyone would enjoy a system where their weight is suddenly cut in half to go from pounds to kilograms, or even a little more than half, as you see the 26 pounds becoming just 12 kilograms here. No dieting, no exercise, just suddenly your weight has dropped by half. Of course, nothing has happened other than changing units, but still, it's a good argument for switching to mass in kilograms rather than weight in pounds. And then finally, an outside temperature of 22 degrees Celsius. That's a nice warm day, 72 degrees Fahrenheit, late spring, early summer, early fall in our area, as opposed to 22 degrees Fahrenheit, which we also tend to see in the winter here in the Bennington area. So the standard unit of measure that we use in science, the metric system, or the SI units, Système International, from the French there, are based on, again, an understanding of common units. So we all agree to use meters for length, or if it's a smaller length, centimeters or millimeters, or even smaller yet in chemistry. And that allows scientists around the world to compare data. If we were using different units, things could get complicated and misunderstandings happen. There was a probe launched to explore Mars not too long ago, and the scientists did their job. All the units were correct and common, but the engineers, the American engineers, were using the pound-feet nonsense, and the engineers from other countries were using the more standard SI units, and the probe crashed. It was a very expensive mistake, and we as taxpayers footed that bill. So it does matter. Units do matter. In the health professions, lives are in the balance if the units are off. So 1 milligram per liter versus 1 kilogram per liter makes a big difference to that patient. So it is important to be detail-oriented and to pay attention to units. We have these fundamental units and then units based on those for length, mass, volume, temperature, and time. And again, it's the system in use in most of the world, and it's everywhere by scientists. Even the American scientists know that it's more important to have a common unit system than to try to impose inches and feet on the rest of the world. So we see here in this slide that the metric units and the SI units don't always align. And so if we look at the metric unit for length and the SI unit for length, they're both the meter. And again, we have the prefixes that will help us with small or large things, smaller things like centimeters or millimeters, larger things like kilometers. For volume, in the metric system, it's typically the liter, whereas the SI unit officially is the cubic meter. Volume is not a fundamental measurement. It's based on length and width and height. So it's a three-dimensional unit, which is why you end up with the meter cubed, or the cubic meter, in the SI unit. For mass, the gram is commonly used in the metric system, whereas the SI base unit is the kilogram. Again, 1,000 grams, just with that prefix that we'll come to know and love if we don't know it already. Temperature for the metric system is Celsius, and that's what most of the world reports their daily temperatures in. For the System International, the fundamental unit is Kelvin, because that is an absolute scale, where 0 should mean 0, although it's not quite exact, as we'll discuss briefly in the future. And then finally, time. Time, fortunately, is familiar to all of us, right? Around the world, we use the second as the base unit, and that's both the metric and SI unit for measure of time. Alright, so looking at our length measurements, length is measured using a meter stick or a yardstick here in the US, and again, a meter stick's slightly longer than a yardstick because a meter stick is about 39.4 inches. So that's why that meter stick's a little bit longer than our typical yardstick. They use the unit meter in both metric and SI systems, so it is a common fundamental measurement of length. And centimeters tend to be used for smaller things, and if we look over at the blown up image there to the extreme right, we see that 1 inch is 2.54 centimeters. So that's if you just multiply quickly by 2.5, you get a rough idea of that conversion of inches to centimeters. So if you have 10-inch feet, then they would be 25.4 centimeter feet. So there we go. It's not too bad. It just takes a little getting used to if you've never dealt in metric or SI units before. Now, some of these useful relationships I would provide for you. I don't expect you to have that memorized, that 2.54 centimeters equals 1 inch. So when we move between what's known as the English system here in the United States, even though England doesn't use it, it's still called the English system from our colonial heritage. So if we're moving between English units like inches or pounds and metric units like meters or centimeters or kilograms, then I would give you the conversion factor. If we look at that second item, though, 1 meter equals 100 centimeters, that I would not provide, because that's one of our goals here, is that you get a handle on these prefixes. So if we're moving within a system, either within the SI or metric system or within the English system, I would expect you to know those conversions. And again, typically we don't move within where like 1 yard equals 3 feet. We don't deal in the English system very much. So more commonly it would be figuring out what those prefixes mean in the SI or metric systems, so that you could go and convert between things like meters and centimeters and kilometers. The third item and the fourth item, again, they're moving between the English and metric, so I would provide those relationships were they asked on an exam. Okay, so we talked briefly about volume before, but volume is the space occupied by a substance, right? One of the definitions of matter is that it has mass and volume. So we have the unit of liter, which is common in chemistry because we're commonly dealing with liquids, and so liquid measurements tend to be used. It's the liter for the fundamental unit for the metric system. Recall that the SI unit is officially the cubic meter, but we commonly will use the liter, which is not officially SI, but it does work well for us. And you can see there the graduated cylinder. We can read using those markings. We know we have more than 900 and less than 1,000 milliliters. So if we look at what those marks are, each of those markings correlates to 10 milliliters. So we're just between, say, the 4th and 5th mark, so we're somewhere in between 940 and 950 milliliters. We can estimate to one more digit, and so we can say this is maybe 946 or 947 or 945 milliliters. We have some uncertainty in that last digit because we haven't read that off, we've estimated it, but that's important when you're making measurements in science. You don't just go by what the smallest demarcation is, you estimate one decimal place beyond that, or in this case it's a ones place, but commonly we use smaller volumes and smaller grad cylinders. We'd be able to estimate to the 10th or the 100th of a milliliter for our purposes. And here we have a series of useful relationships for volume. Again, 1 liter equals 1,000 milliliters. I expect you to know that milli means 1,000th, so you would need 1,000 of them to equal the base unit of liter. 1 liter equals 1.06 quarts. That I would provide because it's going between the English system and the metric system. 946 milliliters equals 1 quart. That, again, would be provided because it's across systems. And finally, 1,000 liters equals 1 cubic meter. That's one of the reasons in chemistry we tend to favor the liter. A cubic meter is too large a volume for most of our applications. We tend to be doing small-scale chemistry, and we tend to want to deal in smaller volumes, so liter or less makes a lot more sense than going to cubic meters. So that's why we break tradition and use the liter instead of the cubic meter for most of our chemistry measurements of volume. So if an object has to have a volume, it has to take up space to be matter. The other requirement is that it has mass. So when we think about the mass of an object, the mass is really a measurement of how much material is in that object. It's measured in grams for small masses, and we tend to deal with gram or milligram amounts in chemistry. So that tends to be our unit, either the gram or the milligram. Officially, the SI base unit is the kilogram. And that's far too large for most of what we do in chemistry, and most of what you would do in the health professions, where you're dealing with, say, pharmaceuticals in very, very small amounts, as little as nanograms per liter for certain pharmaceuticals. So kilograms is a little much for most of what we do, so you'll typically see grams or milligrams in this course. And here we see a few useful relationships. Again, a kilogram is 1,000 grams. That's not anything I would provide. But 1 kilogram equals 2.20 pounds. That I would, to allow you to convert between the two systems. And hopefully you've already figured out your body weight in pounds and converted it into kilograms. But if not, that's a good thing to do, just to see why we should all be on the same page with pushing for kilograms over pounds here in the US. And then finally, 454 grams equals 1 pound. That I would provide because, of course, we're moving from the metric to the English system. So now that we've had a pretty good discussion of units, we should also think about how we're making measurements. In chemistry, we typically make our measurements in the lab, and we use whatever equipment we have available. Maybe in elementary or middle or even high school, you use triple beam balances. And they're great, they're inexpensive, and they're pretty reliable measures. We tend to use electronic balances that cuts out all that uncertainty I talked about, where you have to estimate to that last digit. For anything with a digital display, you just read it directly off. You're not estimating like with the grad cylinder previously. So if we look here, we see a nickel being weighed, and a standard US nickel should weigh about 5 grams, and we see this is 5.01 grams, so that's good news. We also have standards. The standard kilogram, if you notice that on the previous slide, it's stored at the National Institute of Standards and Technology, NIST, and that's important that we have some reference. So our units only are meaningful if we're referring to a common metric. So these analytical balances need to be calibrated from time to time to make sure that they're still measuring correct masses, and we want to make sure that if we were to do a face-to-face laboratory experiment, we'd use the same balance each time. In case there was some sort of error, at least it would be present in all of our data, instead of switching from one balance to another for different trials. Okay, moving on to temperature. Temperature indicates how hot or cold a substance is, and is typically measured on the Celsius scale in the metric system, so a little less familiar to those of us who are only used to the English system. Here in the States, we use the Fahrenheit system. In science, we tend to prefer the Kelvin scale, and sometimes in chemistry we'll still use Celsius, but especially when we talk about gases, and gas laws and solving problems involving those gases, we'll always be careful to use the Kelvin scale, because we can get ourselves into trouble very quickly if we use the Celsius scale. If we look here, we've got some values here for that thermometer, which happens to read in both the Celsius and Fahrenheit scales, and so we see that 18 Celsius is 64 degrees Fahrenheit. So that's one conversion, and we do have the capability of converting exactly between the scales. That formula is provided for you on exams. All right, so time is the one that should be easiest for us because you've already been doing it right. Isn't that nice to hear? So time measurement is based on the fundamental unit of the second in the English system, the metric system, and the SI systems. And going back to that idea of having a common metric, we have to have some sort of standard. So there's an atomic clock that measures a second, and it's based, I believe, still on a radioactive decay of francium atom, I believe, is what we define the second by. But that has changed and may change again. But again, we need to make sure that we've got our seconds correct and that we're all using the same unit, and therefore we need some sort of standard, and that's where atomic clocks have become very important in recent years. So here we have some useful relationships for time, and hopefully these are all familiar to you. 1 day equals 24 hours, 1 hour equals 60 minutes, 1 minute equals 60 seconds. And we could certainly have permutations of these values. If I were to ask you how many seconds in an hour, for instance, well, if there's 60 seconds in a minute and 60 minutes in an hour, so 60 seconds over 1 minute times 60 minutes over 1 hour, we could multiply those together, we'd cross out minutes as units, and we'd end up with 3,600 seconds per 1 hour. So from time to time we'll do things like that where we're converting between units, and hopefully it won't be too challenging for any of you out there. Okay, so let's take a moment to see how all of this is going for us. We'll do a learning check here to see if things are coming together for you, or if you're struggling here on units of measure. So for each of the following, indicate whether the unit describes length, mass, or volume. A 10-pound bag of tomatoes is 4.5 kilograms. A person is 2.0 meters tall. A medication contains 0.50 grams of aspirin. And D, a bottle contains 1.5 liters of water. So take a moment and decide if A is referring to a length, mass, or volume. B as well, length, mass, or volume. Same for C and D. And here we have the actual values. Hopefully you hit pause there on the video if you needed an extra moment. Be careful of that in the future if you didn't this time. So A, hopefully you correctly identified that as mass, right? Kilograms are units of mass. B, meters are units of length. C, grams would be units of mass. And D, liter is, although not the SI unit, it is the typical unit we use in chemistry for volume. So hopefully that went very well. Let's try another learning check and see if you did struggle on that past one, see if you're getting better with this unit stuff now. Okay, so here we're not trying to figure out exactly, we're not doing any math here, we're just identifying the measurement that has an SI unit. So for John's height, is it 1.5 yards, is it 6 feet, or is it 2.1 meters? Again, all that we're really looking at is yard, feet, and meters, and figuring out which has the SI unit. Likewise, the race was won in 19.6 seconds, 14.2 minutes, or 3.5 hours, which is the SI unit for time. The third question wants to know the mass of a lemon. Is it 12 ounces, 0.145 kilograms, or 0.62 pounds? And the last question wants to know about the temperature. Is it 85 degrees Celsius, 250 Kelvin, or 45 degrees Fahrenheit? So take a moment, pause it if you need an extra second, and hopefully when we check these answers, you'll be exactly right. Okay, so for the first one, choice C, the meter is the fundamental SI unit for length, and so hopefully that's the selection you made. For number 2, it's the second we're looking for, so choice A was the best answer. For number 3, kilogram is the SI unit for measurement of mass, and for number 4, Kelvin. Remember, Celsius is the metric system temperature unit, but Kelvin is the SI unit and the unit we prefer in chemistry. All right, so hopefully this little subsection on units went well for you, and you're already getting used to them if you're not used to these SI and metric units that we'll use throughout the course. If they are causing you some trouble, just spend a little extra time on them. Get in touch with me, find out if there's some strategies that we can come up with to help you get more familiar with units.